So we got to use our height equation, which is just the blue equation again, S equals S naught plus V naught T plus 1/2 AT squared. We just solve that for time. An interesting thing happens here. Because our V naught is 0 in the vertical direction, this term drops out, which means you get a little bit of an early Christmas present. This is no longer a quadratic equation because that T dropped out. So you've got 3,000 meters minus 1/2 AT, or plus 1/2 AT squared, where the A is negative. And those are the only two numbers you have to compare. So no quadratic formula needed. You can directly solve for T by taking the square root of the T squared. So it turns out to be 24.7 seconds. So these questions where you're dropping something out of an airplane kind of thing, the fact that your initial vertical velocity is 0 is pretty helpful. What's another way in which we could set up a problem so that we have no vertical velocity? Well, if we're not dropping it out of a horizontally flying airplane, we could have a ball rolling off of a cliff, right? So any scenario that involves no vertical velocity sort of simplifies a little bit. It's not a quadratic formula kind of situation, so that can be a little faster to solve. H impact is down here at 0. So we'll set that equal to 0. And here's H naught of 3,000 meters. Yes, we're solving the blue equation for T. We've got our initial height and our final height, so we don't have to solve for either of those. The only variable left is T. So we find that it takes 25 seconds to hit the ground, and we can turn that into a range. If you wanted to write the blue equation, you could say R equals R naught plus V naught in the x direction T. That's 275 kilometers per hour with some conversion factors times T. And then we could have a 1/2 A in the x direction T squared here, but our horizontal acceleration is 0, so it just drops out. So once again, we find that our range is our horizontal initial velocity times time. So 275 kilometers an hour for 25 seconds, you covered 1,900 meters. Oh, sorry, I didn't see it. Does the weight of the object matter? Yeah, it doesn't look like it, does it? It's interesting, huh? Why is that? Because we've got the weight of the object, which is the force that's applied to it, which is our MA. We only need the A to determine the motion, and all the masses are going to cancel out. The acceleration is just G, and it's pointed downward. So regardless of what the mass is, our acceleration is negative G, and that turns out to be all we need to know. So there's that famous experiment where you sort of get a big plexiglass cylinder and you vacuum all the air out of it, and you can drop a feather and a steel ball bearing, and they'll both drop at exactly the same speed when there's no air resistance. So we do have to kind of keep in mind the fudge factor here. We're talking about dropping a bomb in a vacuum. So are we off by a little bit? Certainly. But it turns out the wind is affecting our horizontal velocity and slowing us down, but it's also limiting how fast we can drop, so we're not that far off in the end. Well, knowing that our height, we started at 3,000 meters, and knowing that we are going to cover 1,900 meters here, we've got this triangle, and they've told us where to put the angle. So we'll use SOHCAHTOA. In this case, we're dealing with the opposite value and the adjacent value. So phi, the angle we're looking for, is the inverse of the tangent of O over A, 1887 over 3,000. So there's just a little trick to finish this problem up and find that angle. Okay, now, if you look at the slide we're on slide 18 out of 53. Sounds bad, doesn't it? Well, we've actually covered about 90% of all of the dynamics questions you're going to see on the exam. So we're pretty much done. So the fact that we only have 1 hour to go and 35 slides isn't really scaring me at all. What we're going to do is we're going to kind of breeze through some of the rest of this as time allows, and we'll just try to pick up a few odds and ends in case they show up on the exam. But I really think we've got your dynamics mostly covered at this point. Yeah? So, and if we do buzz on forward toward the end of these group of slides, you'll see that this packet of slides does include vibrations. And according to the exam spec, you guys aren't supposed to be bothering with vibrations. So there's the last 10 slides or so. Another thing that you're not supposed to deal with is dynamic friction. And that's several of the slides here at the end anyway. So really, all told, you've only got 39 slides, not 53. Okay? So we've gone through about half the slides that pertain to civil engineers, but we've really gone through about 90% of the useful information. Some of the information here, such as on impacts, goes into a lot more detail than you're really going to need. In other words, you might have one impact problem. There's really not a need for you to go through 8 slides worth of impact stuff like the mechanical folks would. With regard to dynamic friction, did anybody see a dynamic friction problem on the last round of the exam? There was a dynamics problem for civil engineers, and it did mention friction. So the exam spec said that they wouldn't do dynamic friction, but they kind of sort of did. Well, here's what they did. They gave you an object, and they said it's going to slide to a stop on a surface. And they said the friction force is whatever it was, say 100 newtons. Is that a dynamic friction problem? I mean, sort of. But if I give you the initial velocity, let's say it's 20 meters per second, we're going to slide to a stop, so our final velocity is 0. If you want to know the distance covered, which I think is probably what they asked, so I don't know that much about what they asked, but they kind of made this sound like you had to know a lot about friction to get this done. Well, you know, dynamic friction is really the same as static friction. It might use a different coefficient. What they did, and people don't come to me and tell me word for word what a problem is, but I bet what they would do is they just give you the friction force rather than giving the friction coefficient. If you needed the friction force, then, you know, you could do mu times n, and the n is just going to be the weight, exactly the same as we did it in statics. So we've got our horizontal surface, our normal force is the weight. We can multiply that by a coefficient mu if we want to, and we'll get a friction force. Let's say it's 100 newtons. If I'm going to ask you for the distance traveled, what else do I need to give you in this question? Well, if I gave you time, you'd use that equation. But what if I didn't give you time? You can solve for S without knowing the time, right? Now, you can calculate the time if you need it, but the point is here you don't need it. And if you wanted to calculate the time, you could do, oops, my screen's moving all over the place. Attendance poll, cover your ears. If you wanted the time, you'd use the red equation and you'd find it there. But what is it that we're still missing? The red, green, and blue equations all revolve around you knowing the acceleration. How do we get the acceleration out of this problem? Well, to get from sort of the physical world of, you know, what objects we're dealing with, a tabletop and a block sliding around, to the sort of time stuff like acceleration, velocity, and speed and distance, we need to know the value of A. So how do we find the value of A? F equals ma, right? So our force of friction is the only horizontal force that's slowing us down. So all I got to do is give you the mass, and you're off and running. So I'll tell you it starts at 20 meters per second. I'll tell you the force of friction or allow you to calculate it, And if I give you the mass, you can do an F equals ma and find the A. Once you've found A, then red, green, or blue, take your pick, whatever you've got to work with, find whatever you need. So they did that squirrely kind of thing where they kind of gave you a friction problem, even though they said they wouldn't. But it's not really scary, right? So that's all we're going to talk about with respect to dynamic friction. In the book, it gives you sort of the laws of friction, some principles to go by. They tell you that static friction and kinetic friction are different. Usually when you're sitting still, you got to pull on something pretty hard to get it moving. But once it's moving, once you're in motion, we use the coefficient of kinetic friction instead of static friction. And the kinetic friction value is a little lower. In fact, they used to say that the coefficient of kinetic friction is 3/4 as big as the static friction. But I think they took that statement out of the current handbook. So they're no longer expecting you to sort of estimate coefficients of friction for static versus kinetic, all this mess. Just, they give you a coefficient, go with it. So that's it. So it used to be they give you sort of a static coefficient of friction, and they expected you to remember to reduce it to 3/4 of its value after you start moving, that sort of thing. I don't think they're going to bother with that anymore. So that's friction. You really don't need to know anything new about friction, even if they bring that problem back, which they're kind of not supposed to according to their exam spec. So what are the big things we've got left then? We've got, so we finished projectile motion. Let's just see what else we can knock out here. We should mention that in the projectile motion stuff, this is how they treat projectile motion in the handbook. It's on page 74. And what they tell you is that your horizontal acceleration is 0. Your vertical acceleration is -g. Your horizontal velocity at any given time is your horizontal launch velocity, which is the cosine term of your velocity. So like if we've got our 180 meters per second here, 90 meters per second of that is vertical, and I think it's 157 of that is horizontal. So this is saying your horizontal velocity is the cosine portion of your initial velocity. For vertical velocity, you have to calculate it because we've got this acceleration term in here, but it's your initial vertical velocity minus sort of the effects of gravity. So this is that height equation that we ended up deciding this is actually just another A equals delta V over delta T vertical velocity equation there. To establish the height at any given time, your y value at any given time, which we've been calling h, is y naught plus v naught t, that's v naught in the vertical direction, t, plus 1/2 at squared. So our good old blue equation shows up there, and we kind of mentioned our range equation is based on an initial reading of range, which is typically 0, and our horizontal velocity. So they're saying kind of the same stuff here in this little section that we've been doing. There are no new equations here in projectile motion. It's all just red and blue stuff. So they've got some other stuff in here. These are things you should ignore. Non-constant acceleration problems on the exam are extremely rare, particularly for civils. There was a typo. They had an alpha there. If you look in the current book, it's now an A. This should be an alpha because this is the Greek version of the equation. All this is saying is that the velocity is the integral of acceleration, whether it's rotational or linear, and position is the integral of velocity, whether it's linear or rotational. You're not going to do much heavy integration work on the exam. The only time they would ask you to do that, it would be sort of this abstract situation where they kind of say, here's an acceleration equation, integrate it, and find velocity. It's just kind of a math question. It's not so much an applied engineering question. Here's particle kinetics, where they tell us that F equals ma. Not too exciting. Now there's one interesting thing that shows up in here that they don't actually mention. You see this little mass times velocity right there? That turns out to be something we call momentum. They do a terrible job in the dynamics portion of the handbook telling you what momentum actually is. It's in there, they just don't actually directly reference it. What ends up happening with this whole momentum thing is we can take F equals ma and sort of work backwards to momentum. The acceleration can be thought of a change in velocity with respect to time. That's essentially our red equation. And if a mass is changing velocity, that can be thought of as a change in momentum. So mv is momentum. So a force causes an object's momentum to change with respect to time. That's no different from saying F equals ma. We've just sort of rearranged things a bit. So what's missing from this discussion in the handbook is that this little mv tucked in here is actually something called momentum, which we designate p. They do have a section on page 75 called impulse and momentum, but they don't really tell you what impulse and momentum are unless you get really good at decoding this sentence in here, which is really cryptic stuff. Talking about this equation, they say the first term on the right side of the equation, that's here, is the linear momentum of a system of particles. So the mv of all the particles is the momentum. That's actually the only place in the handbook where they sort of give a definition of momentum. And then it says the second term on the right is the impulse. That's actually the only place in the handbook they define impulse. Well, let me show you how I would write this. I would say that P equals mv. And a change in momentum is provided by a force over a given amount of time. F times delta t is what we call impulse. So if you see the term impulse, and for civils, I really don't think you will, but that's impulse, F times delta t. And the idea is there, if I want to change a mass's velocity, I can use a small force over a large amount of time, or I can use a large force over a short amount of time. And using either of those methods, I can apply the same amount of impulse to change its momentum, which means change the mass's velocity. And I can sort of rearrange this and say m delta v over delta t equals F, or ma equals F. So there's really nothing new going on here but F equals ma. So this stuff's not really that useful. If you know F equals ma, you're probably in pretty good shape. Well, if that weren't enough, here's another section for you where they tell you that A equals F over M. Yeah, not all that enlightening, is it? So here's A equals F over M, and here's A equals F over M, and there's A. They're a little redundant, aren't they? Well, what they do clarify for you is that if the force is changing with respect to time, then you'd have to integrate this acceleration to get velocity and position. But if the force is not changing with respect to time, then you get the red equation, and if you integrate that, you get the blue equation. So not a single new thought going on in the one-dimensional motion of a particle section. On page 72, they told us that normal acceleration is minus r omega squared. The minus sign indicates we're accelerating toward the center of the circle. That's how the string would pull on a rock if we swung it around. So why do they have to have a whole other section here to tell us that the normal force, well, it's just adding an m in front of the a. So it's mv squared over r. Okay, but instead of r, they use rho because they're really annoying. So our r omega squared is the same as v squared over r, which is the same as v squared over rho. No difference, no significance at all to the use of the letter rho. So we're not having much trouble ticking these things off as we go past them, are we? Let's look at a sample problem. This is an example of the kind of problem where these concepts of momentum, force, acceleration, and velocity, and time all get juggled around. The P is just another mv. If we had impulse, that would just be F delta t. So we can kind of give you any of these and ask you for any of the others. This is an example of a question that involves that. We have a car. It's a Volkswagen Scirocco, and it's got a mass of 800 kilograms. It's moving at 130 kilometers per hour. I've already converted that for you to 36 meters per second. That's its initial velocity. It's going around a curve of radius r equals 135 meters. What's the centripetal force? Well, if you ask me for a force and you give me a mass and velocity, I immediately think F equals ma, and I start wondering which a, how to describe the a. Since it's centripetal force, we're looking for the centripetal acceleration, also known as the normal acceleration, and I've got a choice. Am I going to use v squared over r, or am I going to use r omega squared? I could look up and find either one in the handbook. Well, in this case, I've been given a v of 36 meters per second. So there's really not much reason that I would convert it and use r omega squared. So I can complete my equation here by writing F equals m v squared over r, and punch in the values: 800 kilograms, 36.1 meters per second, square it, and divide it by 135 meters, and I get 7,723 newtons. Which begs the question, what's a newton? If you follow my units here, you can find out. But you probably already know, don't you? It follows the pattern of Newton's second law, F equals ma, where the force unit of Newton is the mass unit of kilograms times the acceleration unit of meters per second squared. So a Newton is defined as a kilogram meter per second squared. And if you look carefully at what I did here, there's the kilogram. Here's meters squared divided by meters, so that's a meter, per second squared. So kilogram meters per squared is what we get, but we know that equals a Newton, so we give our answer in newtons. So as a sample problem for dynamics, this problem's not all that scary, is it? Certainly once I figured out what to do, it didn't take a lot of time, so that's a plus. So the key to solving a lot of problems is correctly identifying what you've got. Once I know that's a mass, a velocity, and an r, pretty much see an mv squared over r to get my force, right? So correctly labeling what you see in the problem statement leads you to the right path pretty often. A lot of dynamics problems, as we mentioned the other day, are very similar to statics problems. In every statics problem, we know the acceleration is 0. Well, what if we let acceleration be the unknown? Then instead of asking you about a missing force, we'll just ask for the missing acceleration instead. So we'll give you all the forces and ask you for the acceleration. Let's see if you can combine that with everyone's favorite, a pulley problem, and solve this problem on this page. The question in the chat window, when do you use A sub n versus A sub t? A sub t is tangential, so that goes along with our V sub t and our S, which is kind of an S sub t as well, right? That's kind of the straight ahead. That acceleration is the acceleration of a car pushing you forward as you drive around a circular racetrack. It's tangent to the circle you're on. A sub n is that normal acceleration. That's what gives rise to the tension in a string as you swing a rock around, a rock tied to the end of the string. It's also what gives rise to the force of the car pushing on your shoulder or your derriere as it's trying to get you to follow a curved path. So it's the n is for normal to your path, and the t is tangential to your path. See, we're not just picking on you, Kenny. I promise we were picking on someone else named Kenny. Oh, Kevin. That's right. It was Kevin we were picking on. How could I forget? So in this problem, we saw some pulley problems where we give you a weight and we ask you for a force. The subtext of that problem was that the acceleration was 0. It was a static situation. Well, if I give you both the weight, or the mass, and the force, then I can start asking you about the acceleration. So that's all we've done here. So when we set up our statics problems for pulleys, pretty much ended up looking at one of our 3 equations of motion, and we can do the same here. We'll look at our sum of forces in the y direction equation. In statics, that had to be set to 0, but here, in dynamics, it's just set to ma. Then we'll total up all of the forces. We've got sort of this stuff moving up and down. There's a minus mg pulling us down, and there's a plus 2f pulling us upward. So see if you can solve that for A if you haven't already. So, Kenny, I've got to ask, do you still get the they killed Kenny jokes like as much as you did 10 or 15 years ago, or have they subsided? All the time. Still not getting old, right? Of course it does. And everybody laughs like they're the first one to say it to you. Why 2F? Remember, our job with a pulley problem is to draw a free body diagram of the stuff that moves up and down with the weight. So we've got this rigidly attached to the weight. We want a free body diagram of this whole thing. We've got our mg in a minus direction, pulling us down. And we've got one length of rope to the ceiling and one length of rope that's going around that second pulley, and each of them has tension F in the rope. So our sum of forces in the vertical direction are minus mg and plus 2F, whereas in statics those would add up to 0. Here they just add up to ma. So we'll do minus 50 kilograms times g, which is 9.81 meters per second squared, plus 2F, which would be a total of 1,500 newtons. And that sort of gives us a total value, and I'm trying to remember what the value is. I'm going to cheat and look at the next page. 1,009.5 kilogram meters per second squared, otherwise known as newtons. So that's our total force. That's an MA. We can kind of divide by the M to get the A. We're dividing by 50 kilograms. And we get an A of about 20. Thank you, Cheryl. Appreciate it. So the answer ends up being D. If there were a third pulley connected, where exactly? Like if there's a third pulley here, wouldn't matter a bit. Yeah, wouldn't change a thing. We're only interested in what's going on with the weight moving up and down. So anything rigidly attached to the weight and moving up and down with it is all we really need to do. Any other pulley is just changing the direction of our tension. It's not sort of multiplying it again or anything like that. Okay? So that's one type of problem you might have. And in this case, it's a pulley problem. It could just as easily be a truss problem, or I don't know, what else. Anything we saw in statics, where you saw a set sum of forces equal to 0, you could see it here, where sum of forces are not set to 0. And we just give you all the forces and let you tell us what the acceleration is. So here, this slide just has a write-up of what we just did to find that one. This is kind of a classic problem. The cannonball problem. In this case, it's a slingshot. It could just as easily have been a cannon. So we've got the mass of a small object. We've got a delta V of 76 meters per second. We've got a time, a delta T. And we're asking you for the force. What are we going to do with these? Well, if I'm asking you for a force, you ought to be thinking F equals ma. And A is a delta V over delta T. So we'll just put 0.046 kilograms times 76 meters per second divided by 1/25, which is 0.04 seconds, and that'll give you the force. So as we mentioned, there are several problems that often come up where we're juggling force, velocity, momentum, time, that sort of thing, and this is one of those. You could treat this as a momentum problem, right? We could say force is the change of momentum over time, and you could calculate a value for mv, or m delta v in this case. But it's really not that interesting. What we're looking for is the force, so just go directly to that. Now, I want to kind of get to the cannon problem, then we're going to touch on the momentum problem, then we're going to talk just briefly about mass moment of inertia. Here's the cannon problem. Mass of the cannon, mass of the projectile, and the final velocity of the projectile is 600 meters per second. What's the initial velocity of the projectile? 0, right? What's the initial momentum of the projectile? Also 0. And the initial momentum of the cannon? So our initial momentum is 0 for the entire system. Well, here's what you got to know. When objects interact with each other, and they don't interact with any outside entities, the momentum doesn't change. So we call this conservation of momentum. In this case, we have a cannon and a cannonball. Those two make up our system. And there's nothing else interacting with them. We're not considering wind resistance. We're not holding the cannon down. So momentum is going to be conserved as these two objects interact with each other and only each other. Well, if the initial momentum is 0 and momentum is conserved, then the final momentum must be 0. What's the final momentum of the projectile? It's m of the projectile times v, so that's 10 kilograms times 600 meters per second, 6,000 kilogram meters per second. So those are the units on momentum if you ever needed to know it. Kilogram meters per second, m times v. Well, the total momentum of the cannon has to be equal. In fact, it's equal in magnitude and opposite in direction, as it turns out. So the mass of our cannon is 2,000 kilograms. What's the final velocity of our cannon going to be? Crickets chirping. Yeah, 3 meters per second. In fact, if we were to be a little more rigorous about this, we'd call it sort of a negative 3 meters per second to indicate its direction. So the cannonball goes off to the right at 600 meters per second, and the cannon goes to the left at 3 meters per second. Now, we've got a little more information in this problem. It says it takes 0.007 seconds for the projectile to pass through the barrel. So this event, this interaction between these two objects, takes a small fraction of a second. We'll use that to ask you this question. I'm sorry, that is the question we already asked you. Down at the bottom here, what's the average force exerted on the cannon if you want to keep the cannon from moving? Well, if I ask you for force, you should write F equals ma. And the A is a delta V over delta T, and we can go one of two directions with this. We can say, well, the delta V of the cannon would have been 3, so we can say mass of the cannon times the 3 meters per second it instantly attains that we've got to hold back, divided by the delta T of 0.0007 seconds, and that would work. Here's sort of what's actually going on. Do you see that this top term here is momentum? Well, the force we've got to hold back is actually the momentum of the cannonball. Happens to be numerically the same value as the momentum of a cannon. So what we're doing here is we're saying the force it takes to keep the cannon from moving has to do with the momentum of the cannonball. 10 kilograms, 600 meters per second, gives you exactly the same answer and exactly the same number. None of this stuff has to make 100% complete, perfect sense to you. We are trying to kind of breeze through this, so I don't want to bog you down with this stuff. But this ends up being kind of another case where I ask you for a force, so you write F equals ma. And then you can sort of juggle things like momentum and velocity as needed to sort of get where you need to get to solve for the force. Work and energy stuff, I think it's going to be a really sort of a small subject for you. Here's a box. If I move the box 10 meters in that direction by applying a force to it, it's a 20 kilogram box. And let's say I apply a 10 Newton force. What's the work done on that box? Well, the work is the integral or the total of the force applied and the distance covered. If the force is constant, we don't have to integrate to get our answer. We just have to multiply. So most often, if you need a work value, it's just going to be a force times a distance. We can call it delta R since they're using R here. So it's 10 newtons times 10 meters, 100 Newton meters of work. You notice anything interesting? How can I tell you how much work was done without even discussing the 20 kilogram weight of the box? Well, if you really delved into all of this, the 20 kilogram weight of the box determined how much force I had to apply. But I already told you the force. So you can skip the whole discussion of the mass and we'd have to figure out how the box accelerates and then slows down and all this stuff. You get to skip all of that. I gave you the force. So just multiply the force times the distance to get the work. Yep. So we've already accounted for that. So that's work. So what are we doing when we do work on something? We're putting energy into it to get it to move. If the box speeds up, then we could say at any given moment, taking the velocity of that box, we can find its kinetic energy. Using kinetic energy equals 1/2 mv squared. And they do use the letter T often to describe kinetic energy. So we could take our 20 kilograms and multiply it by whatever velocity we reached at some point, and we could find the kinetic energy. What if instead of moving in a straight line, we're actually moving in a circle? So let's say I have a turntable here, and I'm going to rotate that turntable a certain number of degrees or a certain number of radians theta. Well, the kinetic energy is based on I omega squared instead of mv squared. So we're about to have a long and winding discussion about what I is. Well, you know where the omega came from, don't you? We're pretty well accustomed to the idea that we can translate equations and turn a v into an omega. But we've got to translate this m as well. All right, well, what does mass tell you about an object? Essentially, mass tells you how difficult it is to move something in a straight line. Due to F equals ma, specifically, the mass tells you what force you need to apply to accelerate something. In rotational terms, we need mass moment of inertia to tell us how difficult it is to rotate something. So as we go about translating equations from linear to rotational, anytime you see an m, it's going to turn into an I. Now, you could do some fancy algebra here, because we know that v equals r omega, so v squared is r squared omega squared, and we know we've got an omega squared there. So 1/2 mv squared is kind of like saying, I didn't leave room for the 1/2, 1/2 mr squared omega squared. Did you follow that? It's a little bit important, so I'm going to do it again. 1/2 mv squared. I know that a v equals r omega, so a v squared can be called an r squared omega squared, so I can write 1/2 m r squared omega squared. Those are the same, right? How does that compare to this? Or more importantly, what is I? So if this is the same as this, what's I? The mass moment of inertia of an object is the mass of that object times the radius squared of the curve you're spinning it around. Mass moment of inertia tells you how difficult it is to get something spinning in the same way that mass tells you how difficult it is to get something moving in a straight line. So as we translate these things, our m becomes an I because our v squared became an omega squared. And as we kind of showed, the r's all cancel out, and this translation does work. So that's cool. If it's a point mass, then every bit of that mass has a single value of radius. Let's switch to a whiteboard here where we have a little room to work. And we'll say you're standing here, and at the end of a long string, you've got a mass. If that mass is pretty well concentrated, then we can basically say every bit of this mass is at radius r. And the difficulty we would have spinning it is summarized as I equals mr squared. Well, what if the situation changes such that we're on a very short string, but we've got a very big mass on a relatively short string? What's the problem now? We could consider that big giant mass to be a collection of a little bit of mass at radius r, a little bit of mass at radius r plus half the diameter of the ball. There's a little bit of mass over here that's really close to us. That bit of mass is going to be easy to spin. And so what we'd have to do would be kind of subdivide this into a million little particles of mass so that we could account fairly for the mr squared of every little piece of it. What we're talking about doing is integrating over the entire volume of the ball. So do you see how things are simplified if it's a point mass? Everything has the same radius value. If it's not a point mass, then we've got to do sort of a I for this particle is its mr squared for that little guy right there. But then this guy out here has a different r value for its r squared. So that's, I for the 500th particle is way out there. We got to integrate all these together. So you end up doing this sort of double integration of the mass with respect to r. And nobody wants to do that. Fortunately, someone has done that for you. For a couple of simple shapes, a couple of simple volumes that is, someone has already gone through that task of describing and integrating up where all the mass is, and we don't have a handbook in here. That's gonna want to set us back a moment. Maybe not. There it is. So let's look in the handbook in the end of the dynamic section. Holy cats, I got it on the first try. At the end of the dynamic section, I think we're on 78 here, 79, page 79. Here are a few solid shapes for which some nice people have already gone through and done some integration. And what they can tell us is that if you spin a sphere, that's a little difficult to say, about its own center, if we were to go do that nasty thing where we integrated up the mr squared for every little bit, the total result of that would be that the mass moment of inertia about a sphere, or for a sphere, spinning about its centroid, let's zoom in here, and we'll point out that they've defined a coordinate system, x, y, and z, all based at the center of that sphere. And then they tell us that the mass moment of inertia for rotating about our x-axis, which does go through the centroid, so it is our x-centroidal axis, is 2m r squared divided by 5. This capital R is the radius of the sphere. You can see it labeled there. Now, because it's a sphere, it doesn't matter if you're rotating about the y-axis or the z-axis, you get the same value either way. And because they've defined our coordinate system as, the 0x value goes through the centroid, the 0y goes through the centroid, there's sort of no difference between rotating about the x-axis and an x-axis through the centroid. Those are identical concepts. However, in some of these figures, there is a little bit of a difference. For example, here, let's go up to this one. Here's the y-axis over here at the end. Considering a y-axis that goes through the centroid would be here in a different location. In fact, the difference between those axes would be L divided by 2, half the length of that rod. If we're spinning that rod about the y-axis, the y-axis that they've defined over there in the edge, then it's kind of hard to spin it. A third of its ml squared. So m is its mass, L is that length dimension. We're going to take ml squared and divide it by 3. That tells us how hard it would be to spin it about the end of that rod over here. But it's a little easier to spin it about the center of the rod. So if we drew a y-axis through the centroid, so there's the sub C for centroid, it'd be a little easier. In fact, this value is 1/4 of this value. So it's easier to spin this thing about its center than it is to spin it about some more distant point. How they find these values? Well, they integrated across the entire shape of the thing and figured out where the sort of average location of the mass would be. Well, that's a reasonable thing. What if we kind of considered this this rod? Could we somehow describe that for the sake of convenience as a point mass? If it were a point mass, still having mass m, what kind of string would we have to put this thing on to make it just as difficult to spin? Well, it turns out if we took a point mass and put it on the end of a string, we can find an R value for that. It kind of tells us the same thing that this I value does. A little shady, little strange concept, but that's the idea behind radius of gyration. If we considered it a point mass, and if we put that point mass on a string of length and the length of that string were L squared divided by 3, then it would be just as hard to spin that point mass as it is to spin this rod. So radius of gyration is a strange little concept that's kind of about summarizing this three-dimensional object as a point mass. The weirdest thing about radius of gyration is that when they give you a table of values, I guess they didn't like typing square root symbols, so they give you radius of gyration squared in the table. So what they're saying here is that R equals square root of L squared over 3. They just wrote it as R squared instead of using the square root symbol. Let me zoom out just a little bit. So radius of gyration is very similar to mass moment of inertia. It kind of tells you how to pretend you're dealing with a point mass. Well, mass moment of inertia just goes ahead and gives you the answer of how difficult it is to spin it. And it turns out the only difference between the r squared value and the I value is an m. So it kind of looks like I equals m r squared, doesn't it? A little hard to wrap your head around a lot of this stuff in the time allotted, but we do want to give you sort of just a glimpse of this stuff. What this all goes back to is trying to figure out how difficult it is to spin a mass. If you're spinning a mass, you can't just consider the amount of the mass, you've got to figure out where it is. If it's far away from you, and you're going to have to spin it about a really large circle, it's going to be really difficult to do that. So it depends not just on the mass, but it depends a lot more, in fact, in a squared sort of way, on the radius of the circle you're trying to spin it around. Now there's one more thing we can do with this. What if we have, in our example here, and I want to draw your attention one more time to this equation for a sphere, 2m radius of the sphere squared divided by 5. Just note that I'm going to use that equation here in a moment. I'll write it right here. I, y centroid for a sphere. Oh, I actually kind of want to go, can I get my old whiteboard back? Okay, I didn't leave much on it, but I can get this one back. I, y centroid of a sphere is 2m radius of the sphere squared over 5. That's just, I'm copying that equation down. So we said if we've got a point mass on a long string, I is mr squared, where little r is the length of the string. If we have a large mass spinning about its center, well, then we consider the shape of the mass. If it's a sphere, then I equals 2m r squared over 5 for a sphere, and for other shapes we could look at the table. What if we have a sphere, but it's spinning about something other than its centroid? What do we do then? Well, we could go through and do a lot of integration. Yeah, right. What we'll actually do is total up the two of them. The total I value for this is the I value for spinning it about its centroid, plus the consideration of the length of the string we put it on. And that is the parallel axis theorem. So, to spin something about an axis other than its centroid, you take the centroidal I value, the centroidal mass moment of inertia, and you add to it an mr squared, where that lowercase r is the length of the string you're spinning it about. It's the distance between our current axis and that axis we started with through the centroid. So that allows you to take a known I value, like 2mr squared to the fifth, or divided by 5, and sort of adjust that for a different axis. So that's the parallel axis theorem. What we're doing in this case is we're saying, well, that lowercase r value is 0, so we've got sort of this plus 0. What we're doing in the first case up here is we're saying the capital R value is really, really small, so our 2m r squared over 5 value is so small we ignored it. We considered it to be a point mass because the radius of that mass is really tiny compared to our r. So the truth of the matter is, this is always right. It's just sometimes we're interested in this because the second one's small, and sometimes we're interested in the second one because this one's small. That's mass moment of inertia. Area moment of inertia, he said, racing the clock, tells us something about not the distribution of a volume or a mass, but the distribution of a cross-sectional area. So here's a cross-sectional area. Area moment of inertia is also given by I. It follows the same parallel axis theorem rules. You can take an I for a centroidal value and add to it an mr squared. Give you an example of that. If we have a circular cross-section, and we know its area moment of inertia about its center, then that would be an IC value. But if instead of bending it about its center point, we're going to bend it about this axis, then we need to know this distance. We can call that distance d, or we can call that distance r, and we can do an mr squared or an md squared, either one. Let's look in the handbook. And, well, first of all, why do we need an area moment of inertia? Mass moment of inertia told us how hard it was to dynamically spin a solid object. What is it we might need to know about a two-dimensional cross-section? What we're interested in with area moment of inertia is how difficult it is to bend a cross-sectional shape. So where you see this come up is in something like an I-beam. And we're going to weld this I-beam to the wall, and we're going to push down on it, and it's going to deflect. And I will give you the dimensions of the beam, and I want you to tell me how difficult it is to bend this I-beam. That would be a hardcore mechanical engineering question, right? Let's see what the handbook has to say, and this will just give you an idea of where this is used, though your questions on it won't be that difficult. We have to consider this cross-sectional area of this thing, how difficult it is to bend that cross-section. That is, we're going to be stretching the top of it and compressing the bottom of it. In this case, we're bending it about its centroidal axis, so we need an I sub c for that I-beam cross-section. Well, that's a little harder to calculate. If it were a round cross-section, we could get the value straight out of the handbook. So let's look at that. Oddly enough, while the mass moment of inertia is discussed in the dynamic section, since that's where it's used, you would think that the area moment of inertia would be discussed in mechanics of materials, because that's where we talk about bending different shapes and how they bend and deform. Oddly enough, that's not where it is. It's at the end of the statics section. So at the end of the statics section, page, I can't see the page number, 70. Here's a circular cross-section. How do you calculate the area of a circle? Easily enough. Here is the area moment of inertia. So this is another I. And it tells us, as we zoom in here, how difficult it is to spin a solid round rod. Well, if you're going to spin it, if you're going to bend it about an x-axis going through its centroid, it would be pi a to the fourth over 4. They're using the lowercase a as the radius of the circle. So the difficulty in bending this cross-section is pi a to the fourth over 4. If for some reason you're setting that circle on the edge of a shelf and trying to bend it, you might be bending it about the bottom, and they've defined the bottom of the circle as the x-axis with no c subscript. Now it turns out that's 5 times as difficult. So it's 5 pi a to the fourth over 4. So these are values you basically just look up. If you want to take this rod and twist it, which is a little beyond civil engineering, it turns out twisting it is a combination of the Ix and Iy values. So for the Ix centroid, we've got pi a to the fourth over 4. For the Iy centroid, we've got another pi a to the fourth over 4. If we add 2 of those together, we get pi a to the fourth over 2. So twisting is kind of like bending it around both cross sections, functionally. That was a bit abstract, but that's where the J values come from. You're not required to know J. That's polar moment of inertia. Again, we can talk about a radius of gyration. Again, the values are tabulated as their squared values, so don't forget to take a square root. There's the polar one that goes along with the J, and here's the I centroid versions and the I not so centroid versions. So that's a real quick, broad overview. I'm not that worried about mass moment of inertia and area moment of inertia. In fact, if you knew nothing about them and went and took this exam, hey, maybe you missed one question. You know what? You're allowed to miss one question. In fact, you're allowed to miss about 20 questions or more. So whenever you come up against a subject like this and you're like, man, I'm really freaking out because I don't understand that mass moment inertia stuff, yeah, don't worry about it. You're not supposed to get every problem on this exam. You're supposed to get the ones you're good at. So throughout this exam process, don't worry too much about the stuff that's like flying past you a little too fast. Study what you can, review what you can, do what you can do, and get your problems correct. Don't try to get the other 20 that somebody else needs. Okay? So we are out of time. I hope you've had at least as much fun as I have had picking on you. Again, there's a student evaluation to be done before you can get solutions to the dynamics problems. Hey, some of those dynamics workshop problems that I've got for you are pretty complicated. Don't let those things freak you out. Be willing to give those problems a shot and go, I kind of know where to start, but I messed up. Look at the solution and just see if you learn something from them. Okay? You're not expected to be the perfect pros at dynamics. It's not required. Very little dynamics will be on your exam. So don't let it freak you out. As we mentioned, that stuff we covered in the first hour and a half is really most of it. The only thing that I'd like to have gone over a little more maybe was impacts. Impacts boil down to knowing a coefficient of restitution, and then if you look, let's just take a quick look at the reference handbook, and I'll show you where impacts are covered. Where did my reference handbook go? Oh, I'm looking at the reference handbook already. That's like I can't bring up the document. It's already here. This is it. So as we look through dynamics, I mean, there's just page after page. You remember all this redundant stuff we said we were going to ignore? The relative motion stuff we already knew. This stuff you ignore. There's a lot in here to ignore. But the impact stuff, let me just show you which equation you need for that. Here we go. Coefficient of restitution tells you how bouncy things are. Coefficient of restitution varies between 0 and 1. We can describe it using text such as perfectly elastic or conservation of energy, which would tell you E equals 1. Sometimes we just come out and say E equals 1. Sometimes we say E equals 0 when we mean perfectly plastic or things stick together. There's no rebound. So if I give you an E value and I give you the mass of one object and the mass of a second object, and I give you some initial velocities, I might give you an impact problem where I ask you for the final velocity of object 2. Hey, look here. There's an equation for the final velocity of object 2. Plug and play. Pretty much all you need to know about impacts. Given the masses, given the initial velocities, given an E value between 1 and 0, you can find the final velocity. That's it. That's all you need for impacts. If you're hitting an immovable object, it's probably immovable because its mass is really, really huge. So let's say we're hitting the Earth. You could go, well, the Earth, 1 times 10 to the 30th for mass. And if you did that all the way through, you'd actually get a decent value there. This coefficient of restitution thing, and I know I'm going over time, check out if you're not interested, catch it on the video if you need to depart and want to come back to it later. But I am going to describe coefficient of restitution real quick. Coefficient of restitution is final velocities over initial velocities. When a ball bounces off the wall, it changes direction, right? Which means its final velocity is going to be sort of in a negative direction. That's why the 2's switch places with the 1's. That's the change in direction in there. It turns out if you're impacting an immovable object, this equation for E is all you need. You can ignore the masses if one of them is an immovable object and has such a huge mass, because an immovable object such as the Earth is going to start out at a velocity of 0 and end up at a velocity of 0. Now coefficient of restitution just tells you about the ball you're bouncing. Comes in at 3 meters per second, goes out at negative 3 meters per second. That's a coefficient of restitution of 1. So for impact problems, if it's an immovable object, all you need is this, set V2 equal to 0. If you're dealing with movable objects, you can talk about the final velocity of object 1 or the final velocity of object 2 using these longer equations. It's really all you need for impacts. Okay? So that's pretty much everything. It took me a few minutes longer than I'd have ideally liked, but it would be entirely possible for me to take another 3 hours on dynamics, but we're really getting down to the last 5% of what's worthwhile for you in dynamics. So it wouldn't really be worth your time to spend a lot more time on dynamics. In fact, some of the dynamics homework problems, a little iffy for you guys. Learn what you want from them, but don't let those bog you down. They're probably a little difficult, but you've got them for reference. Test yourself with them, learn stuff from them as you see fit, as time allows in your studies. So that's really it, but we do have a request to look at problem 23, so we can do that. If you aren't interested in problem 23 right now, you can take off. If you become interested in it later, we've got a recording going on, which you could come back to. And good luck with your studying. I would recommend that between now and the exam, try to take a practice exam if you can fit that in your schedule. That's really valuable for settling this issue of, do I have enough time to finish this exam, or am I going to be pressed for time? Which raises the question of how much time you can spend on a question, and we agreed a couple of weeks ago that you can spend an average of 3 minutes per question, but that means some of them will take you close to no time, and some of them will take you 6 minutes or 7 minutes, right? So figuring out that average timing is a lot easier after you've sort of done a full-length practice exam. I know it's kind of torture to spend 8 hours doing that, or 6 hours, but it is valuable. So I recommend that if you have the chance. Appreciate the accolades on the class. And remember, with those student evaluations, check the number you see fit, but please do include that optional little comment that will help me understand what we can do better for you. You'll have access to me and be able to ask me questions by going to the School of PE website and looking for the Questions for Instructors tab. That's available for something like 6 more weeks or so. We can't run that indefinitely for practical reasons. Everyone takes their exam at a different time, but I think we run it for about 6 weeks. So if any point in that time you run into a problem and it's really bogging you down, send me the problem, send me the solution, and let me know where you're stuck on it. Thank you very much. Oh, so you thought the coefficient of restitution was just a free-falling thing? Yeah, no, it works horizontally just as well as it works for vertical impacts. If you've got a free-falling body, you can use your sort of projectile motion equations to figure out how fast it's going to hit the ground. Or you can turn its potential energy into kinetic energy, potential energy, mgh, or... So most people learn, come on, where is it? Potential energy, which some people call U, is mgh. In the book, instead of calling it mgh, they call it the weight times your y value, Wy. So if I drop a ball, I can say it initially had a potential energy of W times Y, or mgh. And by the time it hit the ground, all that potential was converted into kinetic energy, which is 1/2 mv squared. That gives you your impact velocity to a coefficient of restitution to figure out how. There are sample problems on that in this problem set. It'll kind of take you through that process. So, what do you want to ask me about problem 23? Is it killing you? Yes, you'll never forget the compression analogy there, huh? We did not forget about vibrations. Vibrations is not something that civil engineers have to know about. So it's a good thing because, earthquakes don't happen. So there's no reason that you would need to know. It's simply not in the exam specification. It is for everybody but you. So don't worry about vibrations at all. It should not be there at all in the exam. If it is, give them the finger and move on to the next question. It's not in the exam spec, so yeah, pick C. Okay, let's see. Well, this is an equation of motion, and it relates an acceleration, a velocity, and a distance covered. For a free-falling, it's our green equation that I'm using here, right? You just have to know the acceleration rate. If it's a free-falling object and you're worried about vertical motion, then it's negative g. If I'm providing an acceleration by slamming on the brakes, then the force of friction against the road is what's causing our acceleration. So, yeah, no, it works. All these SVA, red, green, and blue sorts of equations, they all work horizontally, they all work vertically, and they work in any direction. So in this case, here's our initial velocity. Our final velocity is going to end up being 60. Our distance traveled is going to be s. And they're asking for the acceleration. The value ought to be negative because we're slowing down, right? So we're going to get rid of a and d. And we'll look at the difference in our squared velocities. Forgive me for not writing it in green. It's 2as. And we're going to try and solve that for a. Kind of like that. And we have to convert from kilometers per hour to meters per second. So we've got that happening here. So we can take our final velocity squared, subtract our initial velocity squared, and then there's our 2as. Solve that for a, and off you go. Yeah, so like you say, their description of it in the handbook makes it sound like each of these equations is very limited. It's actually quite the opposite. These red, green, and blue equations are very powerful. You can solve most dynamics problems using those equations. They cover all of projectile motion, you name it. If there's a force causing an acceleration, these equations apply. Okay? If you run up against any other problems later on that are giving you grief, shoot me an email through the School of PE website. I'd be happy to help you sort through them. Until then, have a good evening and good luck with the studying. Adequate preparation is the key. It's hard to fit it into your schedule, I know, but if you can whittle away the time to kind of go through this, work the problems, do some review, leaf through the pages of the reference handbook and get familiar with it, and do that practice exam, you're going to be in pretty good shape. Putting in the time is really key to this exam. All right. Let me know how I can help as you need it. Take care.